Despite our dream to expand human civilization into space, a compelling argument on why this is needed has not yet been effectively made. A century ago, Konstantin Tsiolkovsky foresaw the need for humanity to tap the immense resources of space to meet our growing terrestrial need for natural resources, including energy. Achieving global sustainable energy security is now the world's primary challenge. However, the world has yet to embrace an effective path for providing sufficient sustainable energy per person to eradicate poverty, achieve true sustainable development, and enable a prosperous global middle-class standard of living. Base solar power generated astroelectricity is the only practical path to achieve these goals. Building a global network of astroelectric systems at the scale needed to achieve global sustainable energy security is the compelling argument on why the permanent settlement of the central solar system must now be undertaken to begin the age of astroelectricity. In our industrial culture, energy security means having an affordable supply of the industrial energy needed to provide a middle-class standard of living. To live prosperously in a sustainable manner requires that this energy supply also be sustainable. As everyone now understands, fossil carbon fuels are non-sustainable. For the world to achieve global sustainable energy security, we must all transition to green energy, primarily in the form of green electricity, with a per-person green energy supply sufficient to enable a middle-class standard of living. In terms of green electricity, a European middle-class standard of living requires sustainable energy equivalent to a continuous electrical power supply of 5,000 watts or 5 kilowatts. For perspective, this is the total power used by 5 countertop microwave ovens. For a world population of 10 billion people in 2100, at 5 kilowatts each, the world will need the equivalent of a continuous green electricity supply totaling 50 billion kilowatts, or 50,000 gigawatts. For perspective, this is equal to 25,000 Hoover dams operating continuously. While there is a wide range of terrestrial renewable energy options, we know that the energy supplied by geothermal electricity, biomass, hydroelectricity, wave and tidal power, alcohol made from biomass, and algae cannot be significantly scaled up. This leaves only wind power and ground solar power as the two potentially scalable terrestrial renewable energy sources. Wind power is a diffuse and highly variable power source. For example, this is a chart of the wind power available during all of 2019 to the Bonneville Power Administration in the American Pacific Northwest. Besides the hourly variability, there is substantial wind power seasonal and yearly variability. The same is generally true for ground solar power. It is simply impractical to rely on wind and ground solar power to provide most of the 50,000 gigawatts of dispatchable green electricity needed by 2100. The world currently has around 500 gigawatts of nuclear fission power. Substantially expanding nuclear fission power will require the breeding of radioactive fuel that can also be used to make nuclear weapons. The threat of nuclear weapon proliferation, combined with the challenges of nuclear waste disposal, limited suitable nuclear plant sites, and the risk of nuclear accidents such as the 2011 accident in Japan, makes any substantial increase in nuclear fission power unwise and unlikely. A half-century ago, Peter Glasser invented space solar power generated astroelectricity. What Glasser recognized was that while the space surrounding the Earth appears devoid of anything, it is actually constantly filled with substantial solar energy that we simply cannot directly see. Glasser conceived that large space platforms could collect sunlight, turn this into green electricity, and transmit this to ground-receiving stations called astroelectric plants, where it emerges as astroelectricity. When combined with terrestrial nuclear and renewable energy sources, producing astroelectricity is how we can undertake an orderly worldwide transition to sustainable energy. Each astroelectric system will supply 5 gigawatts of green electrical power, equivalent to 2.5 Hoover dams. This will meet the needs of about 1 million people with a European middle-class standard of living. 8,000 of these astroelectric plants will be built around the world to supply 40,000 gigawatts of power. When combined with terrestrial nuclear and renewable energy sources supplying around 10,000 gigawatts, the 50,000 gigawatts of green electricity needed by 2100 will be available. A typical astroelectric plant will require 164 square kilometers of land. Building 8,000 plants will require about 1.3 million square kilometers. In this map of the Earth, the blue box represents the total land area needed for the astroelectric plants. The white area is where on suitable flat land these plants could be built. For comparison, an all-wind solution will require nearly 60 million square kilometers, and an all-ground solar solution will require over 6 million square kilometers. Clearly, the combined solution of astroelectricity along with nuclear, wind, and ground solar is the best choice. For tens of thousands of years, humans have migrated to find more of the natural resources needed for a better life. For our human civilization to continue to thrive, humans will migrate into space this century to build the thousands of space solar power platforms needed for the world to peacefully transition to sustainable energy. This will require exploring the moon and the asteroids, mining these for the needed raw materials, building immense space habitats and lunar settlements for people to live in safely and comfortably, building an astrologistics infrastructure throughout the central solar system, and finally building and operating the space solar power platforms. It is likely that several million people will be living and working in space by 2100, when the age of astroelectricity will be fully underway.